I don't really have to identify the color.
Okay. That was a big thing in high school chemistry.
Identify the color?
Yeah. It's just basically analyzing the wavelength.
You have to figure out the wavelength, and if you have a gauge that has the visible spectrum, you can kind of guess what the color is going to be. 600 to 700 is the red, orange, 400 to roughly 500 is the blue, and then of course everything else is in the middle. So this is where we're going to talk about the history of the periodic table, how it came about. 1864, Newlands noticed that the elements were arranged in order of atomic mass. Every eighth element had similar properties. Well, that worked good until you get past calcium. As you notice, first two rows, there's only 8. By the time you get around again, there's only 8. After calcium, it goes up to 18. So you call it the law of octaves. Octaves meaning 8. So it didn't work really at all beyond calcium. So we said, no good. 1869, Mendeleev and Meyer independently proposed a different tabulation based on the regular periodic recurrence of properties. This is called periodicity, hence the name periodic table. So Mendeleev ordered everything on atomic mass again. But again, it led to inconsistencies. Nobody knew what was going on. So if you do it according to mass, argon and potassium would switch places. But if you look at the properties of argon, it's pretty much an inert gas, noble gas. Whereas potassium is a metal, very reactive. So that didn't jive with what's going on. Turns out the key is not the atomic mass, it's the atomic number. That's why our modern periodic tables have everything going up in atomic number. The atomic number is the number of electrons and protons. We talk about protons. But it turns out it's the number of electrons, and that's where the chemistry occurs. So that's why if you have the same number of electrons, or similar numbers of electrons, you have similar properties. So elements in a column of the modern periodic table have similar properties. So I already talked about sodium and potassium. Right, this ends in 3s1, and potassium ends in 4s1. Well, it turns out sodium, chlorine, NaCl, which is salt. Thank you. KCl. Anybody know where we can find KCl? Potassium chloride. Salt substitute. So people are on low sodium diets. You go to the store, you get salt substitute. It's potassium chloride. However, if you make a solution of it and inject it to somebody, you can kill them and stop their heart with that. Why do they keep telling me ways to kill people and get rid of bodies? It's what I do. Okay? Okay. In fact, I think a lot of times veterinarians use it if they put the animals, quote, to sleep. They give them a sedative. Because it's a more humane way to use. Well, if you look at chlorine, what elements would you expect to have the same properties as chlorine? Chlorine's in column 7A. You're going to use the Arabic numbers, aren't you, just to mess with me? Okay. Later on, you'll see why I use the Roman numeral ones. Well, they should be Roman numerals. Here. just regular. So chlorine, fluorine, bromine, and iodine, the halogens, have similar properties. So chlorine, by the way, I guess I'm going to record this. Well, as we had the evacuation last Wednesday, was the gas that was released and burning. Fortunately, we didn't breathe any of them. How do you represent elements in a reaction? So you know we can divide it. We have the main group of representative elements, columns 1A through 7A. So the first two on the left and the last 6 on the right. Well, we're going to go back here a minute again. And you know the last column is noble gases. The 10 in the middle, we already said it, in transition, and the bottom ones are the inner transition. The outermost electrons of an atom are called the valence electrons. Those are the ones where all the chemistry occurs. So if you look at sodium, 1s1, 1s2, 2s2, 2p6, 3s1, and potassium 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. Sodium ends in 3s1, potassium ends in 4s1. The valence electrons are the electrons in the highest quantum number. So when we look at the electron configuration, we see which has the highest number. The highest quantum number in sodium is 3. There's 1 electron, so there's 1 valence electron in sodium. The highest quantum number, principal shell number in potassium is 4. 1 electron. So there's still 1 valence electron. It's just farther out. So if the chemistry occurs with just the outermost electrons, they both only have 1 outermost electron, so you figure the chemistry would be the same. So if you get sodium chloride, you get potassium chloride. Next one down under potassium is rubidium. So sodium chloride is NaCl, potassium chloride is KCl, rubidium chloride should be RbCl. Now its outermost valence electron would be 5s1. So that's how you figure out the valence electrons. Let's look at chlorine. 17. 1s2, 2s2, 2p6, 3s2, 3p5. How many valence electrons? Quick. No! Ah! I knew you were going to say that. What's the highest principal quantum number? 3. How many 3's do you see there? You see a 3 here and a 3 here, so you got to add them all together. 7. You didn't have to. Just want to make sure you get how to do this. Okay. Let's go down to arsenic. 33. Right out of 1s2, 2s2, 2p6, 3s2, 3p6. What's next? Four s2. Let's see, we got 10, 20, 3d10, 4p3. Just did it earlier. How many valence electrons? Quick! What was that? 5. What's the highest principal quantum number? 4. Oh, here's a 4. Oh, there's also one here. Just because I got the 3D in the middle, don't get confused. So you had the 2 and the 3 and 5. Which is sometimes, like we said earlier, it'll be written 3D 10 4S2 4P3. They keep the two numbers together. That's why they do that. So to figure out the valence electrons, oh my God, now I got to do all these electron configurations. No. Column 1, all ends in S1, so how many valence electrons? Column 2, all ends in S2, so how many valence electrons? Column 3A ends in P1, but we have 2 S's and a P, so how many valence electrons? 3. Column 4, guess how many valence electrons? 4. Column 5, how many valence electrons? 5. Can I keep going? Column 6, 6. Column 7, 7. And column 8, 8. Which is why I like to use the 1, 2, 3, 4, 5, 6, 7, 8A rather than 1, 2, 13, 14, 15, 16, 17, and 18. Because now I have to look at the column number and I know how many valence electrons, which will be important later on. Because if you had to sit there and I gave you, when we get to Lewis dot structures, let's say drawing Lewis dot structures, and tellurium with 52, reacting with iodine 53, you sit there and have to just drag it all. You know tellurium's in column 6, it's got 6 valence electrons. Iodine's in column 7, it's got 7 valence electrons, and you can start there. All the chemistry occurs with just the valence electrons. Everything else is there, but it doesn't have anything to do with the chemistry. Metals typically don't exist as discrete molecular units, but they're complex three-dimensional networks. If you're talking about a metal in an equation, we use its empirical formula. So if I talk about sodium in an equation, I just use its formula, Na. Its symbol. Iron is Fe. For nonmetals, well, there's certain polyatomic ones. Remember, we talked about the diatomic molecules. You have to know those. Hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine all exist as bimolecular, or diatomic. Diatomic is what I was thinking of. Phosphorus can exist as P4. Sulfur exists as S8, but in chemical formulas we just use S for sulfur. Noble gases, we just use their symbols. There aren't too many equations that have noble gases in them because it's very hard to make them react. The metalloids, we also just use their symbols. So for boron, silicon, germanium, and so far we just use their symbol. So really the only ones you have to really remember are the diatomic. Effective nuclear charge. So the nuclear charge, Z, is from the protons, the nucleus. So if I'm just talking about a hydrogen atom on the proton, near the electron, there's an attraction between us. So if we go to helium, electron configuration for helium is 1s2. So now, got 2 protons here. One electron, same distance away. Same effective nuclear charge, same attractive forces. So if we go, let's say, to 3s, now wherever we're at is, he's the electron, I'm the proton. If there's nothing else, there's obviously some weaker attractive force because he's farther away. But not only is it weaker because we're farther away, but what do we got in between? We got people blocking us, so it's called shielding. So even though I would expect a certain attractive force, it's going to be less than what I expect because these people aren't away. Sorry, people aren't away. Okay? So that's called the effective nuclear charge, is the magnitude of the positive charge that's experienced by the shielded electron in an atom. So it's less than the actual nuclear charge. So all electrons tend to shield each other, but the most effective shielding are the core electrons. The core electrons are all the electrons below the valence electrons. So as you go from left to right across a row in the periodic table, the Z increases steadily. Why? This kind of works better. So here is hydrogen. Here's its proton. Hydrogen's 1s1, right? So here's its Thank you very much. Okay. Here's its electron. So there's a force here. We go to helium, 1s2. We now have 2 protons. We have 2 electrons. I'm going to draw them opposite each other, but they're in the same orbit. So what is its effective charge? So this is -1 and a +1. Now we have -1 and +2. So it's greater. So as we go from left to right across the row, we're not increasing the shielding, but we are increasing the positive. So the effective nuclear charge, Z effective, gets bigger. So you see as we go from lithium to fluorine, Z for lithium should be 3, but it's 1.28. Should be 4, but you see as the effective nuclear charge gets bigger as we go from left to right. So the effective nuclear charge is given by the expected nuclear charge, Z, minus sigma, where sigma is called the shielding constant. That question mark should be sigma. I don't know why it didn't come out of sigma there. So the shielding constant is greater than 0, but smaller than Z. So you're going to come up with some number less than Z. Now, as we go from top to bottom, the change is less significant. So, because obviously as you go from sodium 11 to potassium 19, well, we've added 8 more protons. We've almost doubled the amount of protons. So we've got a bigger positive charge. But at the same time, what are we doing? We're adding electrons. So our valence electrons are farther away, plus we have more shielding. So they kind of offset each other somewhat. So the effective nuclear charge changes less when you go down a column as opposed to when you go from left to right across the row. Atomic radius. A couple ways you can measure it. We call this the metallic radius. So So you can think of the atoms as balls sitting next to the other, and you go from the middle of one to the middle of the other. And divide by 2. Or you can go by the covalent radius, where the balls kind of overlap, and you go from the nucleus of one to the nucleus of the other, and divide by 2. There's 2 ways of doing it. The atomic radius decreases as we move from left to right across a period and increases from top to bottom as we move down a group. Okay. Think about this. As we go from left to right across a row, what are we increasing? We're increasing 2 things, but we're increasing the number of electrons, but we're also increasing the number of protons, right? Now, as you go from left to right across the row, even though we're increasing the number of electrons, they're still in the same valence shell, right? Because we have, for example, the second row, 2s1, 2s2, 2p1, 2p2, all the way to 2p6. They're all going to be in quantum level 2. So the shielding, the core electrons underneath aren't changing. You get still the same number underneath. But we've increased the positive charge. So the valence electrons are going to experience more of a positive charge. So what are they going to do? Be attracted more or less? More. So if they're attracted more, they're going to get closer and closer to the nucleus. So as you go from left to right, the atomic radius shrinks. What happens if you go from top to bottom? Well, we already said we're increasing the number of protons. We go from sodium to potassium, we go from 11 to 19. But you're also adding more layers of electrons. So the electrons are getting farther away too. So what would you think the radius would do going from top to bottom? Increase, because you're adding more stuff. A lot more stuff. And you're piling it on top of each other. As you go from left to right, you're kind of putting it next to each other. So there's the general trend you can see as you go across the row, the atomic radius shrinks. It's smaller. And as you go from top to bottom in the column, it gets larger. And that just explains what I just said. Oh, just do there. Oh, there's just an example out of the book. So, if you only look at the periodic table, arrange the elements phosphorus, sulfur, and oxygen in increasing atomic radius. So if you look at your periodic table, look at some relationships. Phosphorus and sulfur. What's the relationship? Which one is farther to the right? Sulfur. Which one is smaller, phosphorus or sulfur? As we go from left to right, we said it decreases, so sulfur should be less than phosphorus. To the right. Look at sulfur and oxygen. As we go down, we said what happens? It gets bigger, so oxygen should be smaller than sulfur. So we said oxygen is less than sulfur. Sulfur, we said, is less than phosphorus. Now, when you take your test, even though it's multiple choice, I've had people do this. Read the question carefully. Make sure you're doing it in the right order, because the question may say, list them from largest to smallest, rather than smallest to largest. And you do the homework, and you see something like, oh, I know the answer. Well, the question asks you for it in the opposite order. And I realize some people, probably not here, but some classes don't realize what that little caret thing means. Point always points towards the smaller one. Ionization energy, IE. Minimum amount of energy required to remove an electron from an atom in the gas phase. So here we have sodium as a gas. We're going to pull off its electron. Ouch. Turns out it takes 495.8 kilojoules per mole. Specifically, that's the first ionization energy. We call it IE sub 1. So that takes the first electron. If we take the second one, and the next one off, it would be IE sub 2. Okay, let's look conceptually about this. So, here's the sodium atom, here's your electron. Holding on to it. So I have to come along and take this away. If I have to deflect that. Okay. So I have to use a certain amount of energy to pull it away. Okay? If I go down to potassium, all right? So now you're the potassium nucleus. Where is your valence electron? Closer or farther away? The atomic radius gets bigger, right? So she was holding on to her, so I had to pull because she wouldn't let go. You, on the other hand, here's your electron out here. So I go to take it away. They can take more or less energy? Less. So they go from top to bottom in a column. Is the ionization energy going to go up or down? Down. Now, going left to right. So, again, sodium. I need to keep them together this way. So she's holding on, right? One electron. So, I'm got to pull it away. We go to magnesium, right? Even though it has S2, so there's two electrons, they're both the same distance away from the nucleus. What did the nucleus get when we went from sodium to magnesium? No, what did the nucleus get? We added another, the nucleus. What comes in the nucleus? Protons. So we added another proton. So now we have two protons. Hold on to the electron. Yeah, you get two of them now. So before, it took a certain amount of energy to pull it away from one. So now I've added more positive charge. It's going to be harder. It's going to be harder. So as you go from left to right, the ionization energy should increase. See? Well, if you look from top to bottom, you see the numbers going down in the column. As you go from left to right, on a trend, it increases. But you see some anomalies there. For example, going from beryllium to boron. It should have went up, but it went down. Uh-oh. What's happening there? So for boron, how many electrons? For beryllium, how many electrons? 4. So 1s, 2, 2s, 2. Okay? For beryllium. Now we do boron, how many electrons? 5. 1s, 2, 2s, 2, 2p, 1. So, which one's going to be easier to remove? Yeah, so it should take, boron should be lower energy than beryllium, and it is. Now after beryllium, We go to carbon, which is 2p2. So now we've added protons, and these are still the same distance away, so it goes back up. We go to nitrogen, it goes back up. What happens with oxygen? We get to oxygen, we have to start pairing, right? So even though these are the same level, remember the cats in the box? So before, up until we got to nitrogen, we had one cat in each box. So to remove it, it didn't matter which cat, the same amount of energy. When I get to oxygen, now I have two boxes with one cat, and I have one box with two cats, and the cats hate each other. So I reach in to pull out that cat. The other cat is going to help me by pushing it. So it's going to take less energy to get that cat out than it would be if it was in the box by itself, which is why it goes down for oxygen. Then it goes back up after that for fluorine and neon. So there is the graph. So you can see lithium, beryllium drops down for boron, and then it goes up for carbon, nitrogen, falls for oxygen, and then it goes back up for fluorine and then neon. And that's repeated. So you can see the general trends. In general, the ionization energy increases, except for those special cases. The first ionization energy. And so there we're talking about group 2A, and we go to group 3A, so that's when we're going from beryllium to boron. We go from paired group in the S to one lone electron in the P, so that's easier to remove. Going from 5 to 6, we have 3 unpaired in the P, and then we have the 1 paired in group 6. So that's like having 2 cats in one box, so that becomes easier. So there's a list of ionization energies. IE1, IE2. Notice how high they go after you get rid of the first one. Well, think about it. After you get rid of the first electron, now you got even more protons per electron, so it gets even harder to get rid of the second one. Much harder to get rid of the third one, fourth one, and you can go all the way up to 10. So each subsequent removal of electron takes more energy. So would you expect sodium or magnesium to have the greater first ionization energy, and we should have the greater second? Now most of you could run your periodic tables and say, oh, magnesium's to the left, so it should be greater. But let's look at the configuration. Sodium's got 11, 1s2, 2s2, 2p6, and 3s1. Magnesium has 12, 1s2, 2s2, 2p6, 3s2. So if I look at these two, so their outermost electrons are both in the 3s subshell. Sodium has 1, magnesium has 2. Which one's going to be easier to remove? Why? Because of that push, right? We got 2 cats in the box. So, what's the question? We should have the greatest first ionization energy. Should be for IE1. Sodium should be greater than magnesium. So, okay, now I'm going to get rid of one electron. So, because we're going for the second ionization energy, so we just removed one. So now, this is what we have with Mg plus and Na plus. Now I'm going to remove another electron. Which one's going to be easier to remove? Magnesium?
Sodium, because it has small.
Oh, E1, magnesium is greater than sodium, because it is to the right. Oh, I was wrong. Magnesium, I know I got it backwards. It is to the right, so IE1, magnesium is greater than sodium. For IE2, it's the opposite way around. Yeah, for IE1, these are both in the same shell, so they're like separated from each other. That only works for the p orbitals, the cats in the box. But for sodium, it's easier to remove this. This is a valence electron. For sodium, now we got to go to the core electrons. It's harder to remove. Yeah, I'm going to stop that right there.